time to start. Okay, so any question from this time? This time we go over this very important concept that will be useful throughout the whole class. That's this convolution. So we derive that for any LTI system, or at least for discrete LTI system, we derive that any discrete LTI system can be characterized by this unit impulse response function, or unit impulse response signal h, and this h signal is defined as the response of the system to this unit impulse signal. So you hear a system with this delta of n signal, and the response is h of n, and this h of n will actually determine the whole system, because for any input signal, you can calculate the output signal y of n as x convoluted with h, x of n convoluted with h of n, and so this becomes another function of n, and its mathematical formula is this. It's a summation of the dummy variable k from minus infinity to plus infinity, then s of k, h of n minus k. So the output variable, the independent variable here is n, and then you sum it over k. And and let's go back a little. So the derivation is that we think the system is linear, so we break x into the summation of different x summation of different points. So x of n as some of different delta functions, with height being x of k. So delta of n minus k being a spike at k, and then the height will be x of k. So just like this, x of n has no spike, and we write it as a linear combination of spikes one by one. And so x is a linear combination of those delta functions, and then y is the summation of the response to those delta functions. And then if the system is also time invariant, then the response to all the delta function is just the time shift of the response to the delta function at 0. So in the end, everything can be determined by this response to delta function at 0. So this h of n equal is this h sub 0, which means that response to the response to the delta function. Okay, so that's a quick derivation of the convolution. Then we go through a lot of calculation of the convolution, and then things get a bit confusing. So we say that k is dummy variable, but if we fix the n, then we want to calculate y of n, then we kind of like this mental picture with respect to k. Okay, so we like to write those h sub k, and then we flip it around to get h of minus k, and then we can do a time shift to get h of n minus k, and we see that h of minus k will have the 0 position at n instead. Okay, so the transformation you do to get h of n minus k as a function of k is kind of you flip h of k around. You do time reversal, so you flip h of k around, then you drag a 0 point to n. Okay, so if you think n is negative, then you push this to the left hand side, and we kind of like to slowly increase n to see where is h of minus k position, and then we want to see how h of minus k is overlapping with s of k, because we are doing this summation over product. So this summation is non-zero only when x of k and h of n minus k is non-zero overlap. And so we slowly increase n to see when x of k and h of n minus k has overlap, and then we can do the calculation. So here is another example. So x of n is this exponential decay starting from n equal to 0, and h of n is this unit step function. Then we see that h of n minus k is like this thing. It's a unit step function at the reverse direction. It's oy and stop at n, and then we slowly increase n, and then see when the h of x of k and h of n minus k has overlap as a function of k. And so in this example, when n is less than 0, those two functions has no overlap. and so the summation will be 0, and when n is greater or equal to 0, then you are summing over some geometric series, and so you plot the y of n and look at this. As n get bigger and bigger, you summing over more and more of this geometric this exponential decay function, and so it's exponential accelerating to 1 minus alpha. Okay, and so we have a whole bunch of examples for this discrete time convolution, and we in this more complicated example we see that oftentimes when your x of k and h of n minus k has multiple boundaries, then you need to do careful case analysis to get different algebraic expressions in different regions of n. Okay, so yeah, so but in the end, that's a lot of calculation, just a lot of I guess arithmetic calculation or algebraic calculation. Okay, and but the general idea, in the end, the idea is very simple. You just calculate this function. You calculate summation k so k h of n minus k, and that should be your y of n. Okay, and so that's for discrete time convolution. Today, not surprisingly, we are going to talk about continuous time convolution. Okay, and so continuous time is not going to be a summation anymore, and it's going to be an integral. And here we give kind of a attack derivation of the continuous time. Continuous time convolution, and it will be we are trying to mimic what happened in discrete time, but this is a bit more complicated because in continuous time it's not so obvious that your signal can be written as a summation of the input signals, but indeed we can, but still we can do some kind of approximation to think that, so that's the end result. We can think our any signal as the integration between your original signal and whole bunch of time-shifted delta function. Okay, and yeah, so that's kind of a result we want to get, and just similar to discrete time, we are going to use linearity and time invariance to say that our output signal is just determined by the response to a delta function. Okay, and but let's go through the derivation of what we think our an input signal is the linear combination of the delta function. Is we first kind of discretize our I guess we approximate our signal with a whole bunch of staircase like this. So we write a whole bunch of staircase with the width of those cases being this big triangle of those triangle. So it's 0 to triangle, 0 triangle to 2 triangle, etc. And so we approximate this smooth function with those staircase, where each stair has with the triangle, and the height is the value of x over t at the left side of the edge here. Okay, and so you look at those staircase function. So the staircase function look at this. Okay, and we think if when the triangle goes to 0, then our x of t will be like will be just like we think if the triangle goes to 0, then the staircase function will approximate our original signal x of t. Okay, and yeah, and those function, if we write it in terms of and those function, so we write it in terms of triangle. The staircase function can be written in this way. So it's a summation of a whole bunch of so the staircase function we can write is a linear combination of each stair, and each stair is a function that has height being x at some value, so say it is minus 2 triangle, and the height will be this x of minus 2 triangle, and but we can express this as our this delta subtriangle function times something. Okay, So for example, when we think about the stair that has the left side at t equal to 0, so we have we have a rectangular here, and so the height of the rectangular should be x of 0, and this x of 0 can be think of as x of 0 times 1 over triangle times triangle. And then the 1 over triangle will be the height of those delta subtriangle, right? So this is the function we use to define the delta function. We say this function, when triangle goes to 0, goes to delta function. Okay, and so we kind of do this convoluted way to write out x of 0. So we say x of 0 equal to x of 0 times 1 over triangle times triangle, and so that this function is this delta subtriangle of t, and times triangle times x over 0. And so similarly, so here we have it. So this function with height being x over 0, we think it is a function. So this rectangular here, we think it is x over 0 times delta subtriangle of t times triangle. And then this rectangular starting at the -2 triangle, we think it is x over -2 triangle times delta subtriangle, and time shifted to -2 triangle, so t plus 2 triangle and times triangle, etc. Okay, so each of the rectangular is time shifted delta subtriangle times some times the signal value x of t at some point, and times the triangle. And so if you sum over everything, then we have that x of t approximated by those staircases are just summation over OK, so different shifts over, so different number of steps here. So x of x of k triangle times the delta subtriangle and time shifted to k triangle, and times the extra width triangle here. So it's just this equation, and go time shifted to different k triangle. Okay, and we think so this is without the limit of triangle goes to 0, this is a staircase function, and we think when the triangle goes to 0, it should go to x of t. Okay. And yeah, so that's a lot of explanation of the ad hoc way of breaking our continuous function into horizontal staircase, and then we take a limit, we can go to our delta function. But before we take a limit, we think about, now this is a linear combination of a whole bunch of signals. Okay, so this is x of k subtriangle. Now this is just a number. So so in this expression, the only product depending on the independent variable t is here. Okay, so we think about how this independent on t is only here. It's this delta subtriangle function t minus k delta. T minus k triangle. And so now by linearity, because it is a linear combination of those delta subtriangle signals, then then the output should be just the same linear combination. So we have the same coefficient x of k triangle, and times some response to this function. So h of t, and with some k triangle. And then this triangle is just the same triangle here. So this is just a number, and we write the number again. Okay. And here we have h sub k triangle t is a response to delta subtriangle t minus k triangle. Okay, and yeah, so this is just some notation. And so we have x as a linear combination of delta subtriangle go to y as a linear combination of the response to delta subtriangle. And then just like a discrete case, we think if our signal is time invariant, I guess the logic here, we take the limit of triangle goes to 0 first, then the summation, so we are summing over something times triangle, and when triangle equals 0, this summation become integration. So x of k triangle, we just rename it as a dummy variable tau. So this is now x of tau, and then delta sub triangle. When triangle goes to 0, it becomes a delta function. This is a very weird delta function. It's just like so. Remember before we say this thing when triangle go to 0 become delta of t, and yeah. So now this is similar. It's just delta of t, and then taking a time shift because k minus delta is tau, so it's delta of t minus tau. And then this tau, this triangle here, when triangle goes 0, become an infinitesimal element of your integration. So this is just d tau. Okay, and yeah, so this is kind of ad hoc derivation of because the hand-wavy derivation of y x of t is the integration of x tau times delta function times d tau. X of tau times delta of t minus tau d tau, and so y here is similar. So this summation become integration. So this x of k triangle become x of tau. Then you have h sub tau of t, then d tau. Okay. And then just like in the discrete time case, we now use the time invariant property. So this h of h sub k triangle of t is a response to delta sub triangle of t minus k delta, and if the system is time invariant, then this h sub k triangle of t is just then for different delta of t minus tau, yeah, so the system is time invariant, so this h sub tau of t is a response to delta of t minus tau, then it should just be a time shift of the response to delta of t. So we think, so we write the response to delta of t as h of t, then the response to delta of t minus tau should just be h of t minus tau. So here this part should be just h of t minus tau, and finally we get the convolution of the continuous time signal is y of t is integration minus infinity to plus infinity x of tau h of t minus tau d tau. Okay, yeah. So this is the derivation of continuous time convolution. It has the same logic of the discrete time convolution, but with the extra element of we have this we break the any signal into the integration of your signal with the delta function. So this is like a linear combination of delta function, but with integration here, with the integration sign here. And but anyway, here is the continuous time convolution formula we like. And we'll use a lot. That's y of t equal to x of t convoluted with h of t equal to minus infinity to plus infinity x of tau h of times h of t minus tau d tau. Okay, and yeah, once again, h of t is a unit impulse response function signal, and it's the output of the system when input is delta of t. And yeah, now this response function is a bit funny because it's a response to this delta of t, which is take another very well behaved signal, is this infinite spike at t equals 0. And but anyway, this is how we define things. And yeah, and this is the convolution integral we will do. Yeah, any questions so far? If not, let us see some example of this convolution integration. Our examples are very similar to the discrete time case. Okay, so here we have a signal, so we have similar things in the discrete time case. So our x of t is this exponential decay function starting from t equal to 0, and our h of t is just a unit step function. And then we can have the convolution of x of t and h of t being the output of y of t. And so similarly, we fix the t and we think about how this integration will go. And so we now plot x of tau and h of t minus tau as a function of tau. And so x of tau as a function of tau is just like x of t, just change t to tau. And now we have h of t minus tau. Then you need to do the change of independent variable, just like before. So we flip these things around and push it to left and right with t. So when t is negative, so you flip this, you do time reversal first. So you get h of minus tau looking at this function. And then you push the 0 point to a left or right by t. And so when t is less than 0, your h of t minus tau look like this. It's a state function that stops at t. And then you see that when t less than 0, h of t minus tau and x of tau has no overlap. So when you do this integration of their product, because their product is 0, the integration is just 0. Okay. And when t is greater or equal to 0, then this function and this function do have overlap. Its overlap is from 0 to t. And so you can do this integration. So you can do this integration for tau from 0 to t, and then the value is e to the minus a tau. So you do the integration, you find out the result is 1 over a 1 minus e to the minus at. Okay, and just like before, we need to be careful about your variables here. So tau is a variable that should be integrated out, and your output. So your your answer here should only be a function of t. Okay, and I believe this is a part of the answer. So when t less than 0, your y of t is just 0. When t is greater or equal to 0, so you have this 1 way. 1 minus e to the minus at, and is exponential saturating function to 1 by a. Okay, and if you want to write those two equations into one equation, you can use this unit step function. Just write this function times unit step function, so that when t less than 0, it just gives you a 0. Okay. Any question? Oh, we are doing really fast. Okay, so this is continuous time convolution. It's very similar to discrete time convolution. If don't have question, then we can go to the next part, which will talk about properties of LTI system. Okay, so there are actually two properties, two sets of properties we'll talk about. And the first property is we want to talk about the property of the convolution operation itself. So this x of t convoluted with h of t, this operation, this is star operation. So this looks a lot like a multiplication sign here, and so this star in the middle of two things. And indeed, we will see that it behaves like multiplication because it's three properties that we know that multiplication has for just a multiplication number. That's commutative, distributive, and associative. And so that's the first set of properties we talk about. That's the properties of convolution. And then the second set is that we now know LTI system is totally described by this impulse response H. And then we can describe all the system properties by properties on this H. And in particular, we talk about memory or memoryless property, and the invertibility, and the causality and stability. And we find out that they all have some if condition that satisfied by H, then you will get your system has these properties. And but you need to remember that those properties only for LTI system. Okay, and so those are the things we are going to talk about the properties. Okay, and so before talking about properties, I should have a slide that want to stress something first. So I guess that's kind of like a property of LTI system. So remember we said that LTI systems are completely determined by this system impulse response H, but we need to be a little careful about this determined by H thing. You need to remember that this is only true for a LTI system, and here we just give a very trivial example where you have different systems that have the same impulse response H. Okay, so let's say we have write down some impulse response H. So if our H is this function that look like two unit impulse summing together. So you have h of n equal to 1, when equal to 0, 1, and 0 otherwise. And so if your system is LTI, then you can totally calculate your output of totally determine your input-output relationship by just doing the convolution. And you see your y of n equal to x of n convoluted with this h of n. So that's x of n plus x of n minus 1. And but you can also have different systems that have the same impulse response, but the system different from x of n plus x of n minus 1, and because you can have a system that's not LTI. And so this is just an example that's saying when you want to determine your system by H, then you need to make sure that your system is LTI, otherwise your system can have a different behavior. And here are two examples of non-LTI system that has the same impulse response H. Okay, so for example, this system, this output, basically this input squared, and also this output being mix of x of n, x of n minus 1. I think it don't give us too much insight to calculate their impulse response, but yeah, you can plug in the input x of n as delta function and see that the output y of n is indeed this function for those two systems. And because they are LTI, they are not LTI, they can be a different system from this system. Okay, so yeah, so this is just a cautionary tale that don't blindly say that your system is determined by your response, by your impulse response, because this is only true for LTI system. Okay, and yeah, so now we are finished with this HR slide. Let's go to the things that we actually say we are going to talk about. So that's the properties of the convolution operation itself. And first we have the commutative property, and that just means you have signal 1 times signal convoluted with signal 2 equal to signal 2 convoluted with signal 1. Yeah. And yeah, so this is quite evident by itself, quite clear by itself. So x of n convoluted with h of n equal to h of n convoluted with x of n. And this is true for any x of n and h of n, and similarly for continuous time. X of t convoluted with h of t equal to h of t convoluted with x of t. And then the proof is not too exciting, so we just say this is true. But if you want to do the proof, you basically just write down the formula and try to do some change of variable. So basically you want to say summation k x of k h of n minus k equal to summation k h of k x of n minus k. And basically you want to change this n minus k to k, etc. Okay. Yeah, I think you can do some change of you can do some change of variable to swap between h of n minus k and k, and you see that you will get the same summation, and here you will get the same integration. Okay, so commutative property is very nice, and it's also funny. It says that it feels like the role of signal and the system is kind of interchangeable here. You will think about a convolution, tells you how you get the output from input signal convoluted with the system the impulse response. Okay, and but anyway, this is true. And then the second property is distributive property, and it's like a distributive property of multiplication. It says that if your system if your impulse response is a summation of two impulse response, so x of n is convoluted with h1 of n plus h2 of n, then that just equal to the summation of the two output together, plus x of n convoluted with h1 of n plus x of n convoluted with h2 of n. Okay, and similarly for continuous case. And here we have some pictorial way to describe this fate. So we say that x of t, if you split, you have this serial cascade of two systems, two LTI systems. So first one described by h1 of t, second one described by h2 of t. So you have x of t input to this system and input to this system, and output get output y1, y2, and add the y1, y2 together to get y of t. Then that's just same as you go through a LTI system that's described by h1 of t plus h2 of t. Okay, so the distributive property, and we can have a pretty short derivation of the distributive property. We assume the commutative property is true. Okay, and so first is that so the proof is a bit funny because the first line looks like already the proof, and the first line says that by the linearity of a system, so convolution is distributive on its first variable. So convolution is like x convoluted with h, and so if you think about, you have x plus x1 plus x2 convoluted with h, then by linearity of the system, that automatically get that this should be x1 convoluted with h plus x2 convoluted with h, because linearity says that your input is x1 plus x2, then the output should be a summation of output to x1 plus output with x1 and output with x2. Okay, so this is just linearity. So if you want to get this, you don't need any derivation. This is from the linearity of the system. Okay, and about the distributive property here, we are doing is a bit different. It's distributed on the second argument here, and so to get distributive on the first argument or distributive on the second argument, you just use the commutative property. So you say this thing is equal to this thing is equal to h convoluted with x1 plus x2, and this is equal to h convoluted with x1 is equal to h convoluted with x2, and then you just change the name of x to h, h to x, then you get the x convoluted with h1 plus h2 equal to x convoluted with h1 plus x convoluted with h2. Okay, so that's a distributive property. It says that in any argument, this thing is distributive. Okay, and then from just linearity and the distributive, I guess from the distributive property, we can we see that we can simplify our convolution of convolution a little bit. Say our x of n equal to this function, so it looks kind of like this. It's 1 over 2 to the n times u of n plus 2 to the n u of minus n. So basically, this the first part is the exponential decaying function when n is greater or equal to 0, and the second part is another, I guess it's an exponential growing function when n is less than 0, and it's like the exponential decay to n equal to n to minus infinity. So x of n is like this function, and your h of n equal to u of n. And now I think about what x of n convoluted with h of n, and here we only use the linearity, but nonetheless, so we think this h of n, x of n convoluted with h of n, then you get some y1 of n plus y2 of n, because x of n is the first part plus the second part, and then the y1 of n will be this exponential decaying function convoluted with the h of n, and y2 will be this exponential growing function convoluted with h of n. And then we already do calculation for both of those examples. So for y1 of n, I think is this example we have x of k look like this, and h over n minus k look like this, and we see that the resulting output is this exponential saturating function. And for the other part, for those exponentially growing x over n, we also calculated its convolution with h over n already, and it's this function that has exponential tail when n is less than 0. And so you have this signal plus this signal together, then you see that the output signal is this signal. So it's you have the exponential saturating part and the exponential decaying part, growing part. Okay. Okay. So here is a bit of example of linearity. I guess it technically don't use the distributive property, but the linearity is very similar to distributive property. Okay. And then finally, we have the third property of multiplication is associative. It says x over n convoluted with the parentheses h1 over n convoluted with h2 over n equal to x over n convoluted with h1 then convoluted with h2, and similar for continuous time. So it doesn't matter about what the order you do your convolution. You can convolute the second, the third signal first, or you can convolute the first and the second signal first, and the result is the same. And proof here, we just skip. We say it's in a homework problem you want to see. And on the consequence of this property, we can just write those expression without any parentheses, and the meaning will be ambiguous. So we can just write a string of convolutions, say x over n convoluted with h1 over n and convoluted with h2 over n, and the expression is ambiguous. And also, the nice thing about this property, and so by this property, we can have that if you want to have your system go through LTI system by H1 and by LTI system by H2, then the same as you just go through a LTI system by H1 convoluted with H2. Okay, so that's from associative property. And I guess by then you use the commutative property, then you see that because H1 convoluted with H2 is same as H2 convoluted with H1, and then you break those two, then you see that from the associative property and the commutative property, actually applying the ordering of applying LTI system doesn't matter, because this applying H1 first, then applying H2 first is same as applying H2 first, then applying H1 first. Okay, so this implies the commutative property of this serial interconnection of LTI system. So that's very nice. Any questions so far? Not, then I guess it's a bit early, but we can I guess let's keep going, and if we finish early today, then we just take a break earlier today. Okay, and so I guess let's have a small recap. So we see that the convolution operation is very like multiplication, and it has this associative property. So the ordering of resolving those convolution doesn't matter. Then it has distributive property, so that you have something convoluted with summation of other things, just same as you convoluted with each component first, then adding them together. And you also have this commutative property that's saying that x convoluted with h is the same as h convoluted with x. Okay. So yeah, you see this convolution operation is a lot like multiplication, and that justify while we write it log like the multiplication of those two signals. But yeah, it's a very complicated kind of multiplication because you are multiplying two signals. Okay, and it's convolution. Okay, and if we are okay with convolution, then let's talk about system properties for LTI system. Okay, and the first property we have is that system is all without memory. Okay, so if you want to determine whether a LTI system is memoryless or memory, then you just look at its impulse response, and then if it's impulse response, so if it's memoryless, the impulse response must look like constant times the delta function, and the constant here just say it's k bar. Okay, and maybe that's time to draw some picture. Okay, let's try. Oh, wait. Yeah, time to draw some picture, and so why didn't I see? This is not responding. That's annoying. Let's see. Do I get this? No, not responding. Oh, here we are. Okay, and yeah, so it's memoryless if only if well, we say h of 0 equals 0 when n not equals 0 means that sorry, h of n is 0 when n not equals 0 means that h of n is a constant multiple of delta of n. So we have n here, and so n here, and so we are saying h of n should look like this thing. So h of n should look like some height k bar here times some height k bar times this delta function, which is non-zero only when n equal to 0. And I think the derivation here should be pretty straightforward. So so you think about this thing h of n should be the response to delta of n, and so so you just basically compare the 0 function and the delta of n function. Okay, and so you have a 0 function as input to an LTI system, then the output should be 0. This is just by linearity. When by linearity we say if we have any linear system, when input is 0, then output is 0. And you think about what's your delta function. So delta of n look like this, right? Delta of n look like this. Okay, and so delta of n is only different from 0 function n equal to 0. So when and you know the output only depends on the function value at the particular point for memoryless function. For memoryless signal. And so for any n not equal to 0, since the delta of n is same as the 0 function, then the output should be just 0. Okay, and so the output of this memoryless signal. So the output of this memoryless so the output of the memoryless system to the delta function can only be non-zero when n equal to 0. Okay, is logic okay? Because delta of n is only non-zero when n equal to 0. So so the output to delta of n can also be non-zero when n equal to 0. Okay, so h of n equal to k bar times delta of n, and so that's for if only if. So that's saying only if this thing we can be memoryless. And so the other direction, if we want to if, then it's actually easier to prove. So we have h of n equal to k times delta of n. Then we can calculate the output y. So you say y of n equal to x of n convoluted with this k delta of n, then k bar delta of n, then that's k bar times I guess our property doesn't say this, but for convolution we also have the property that when you multiply a constant multiple of your signal, then the convolution is basically linear. So x convoluted with k bar delta of n equal to k bar times x convoluted with delta of n. Okay, and yeah, so this is another property we didn't say, but this is true for convolution, and it's very easy to prove because convolution is basically summation or integration. Okay, so it's linear in its arguments. Okay, so anyway, back to our output for memoryless signal. So y of n equal to x of n convoluted with x bar k bar delta of n, and equal to k bar x of n convoluted with delta of n, and then x of n convoluted with delta of n is just equal to x of n. Okay, and yeah, I guess and so that's k bar x of n, and the output is k bar times x of n, and this thing is obviously memoryless because y of n is just a constant multiple of x of n and doesn't depend on any n not equal to 0. And yeah, similarly for continuous time, we will have that the response to delta function should just be k bar times the delta function. And then you do a very similar convolution, you get that y of t will equal to k bar x of t. And yeah, I guess we are a bit missing on the convolution with delta function being just the same function itself. So we can try to have that next class. Yeah. So we'll take a break now, and we'll go to this detail a bit more later, next class. Okay. Yeah. So let's take a 10-minute break.这个是我可以读。看到。我才思考，就是看到一个就是T类是可以比output类是还要短的一个数字证明，就是用那个就是用那个马克黄那个 pass recall 结构的那个 TRE， 就是有人要做一个。就是说，它的 T 类是可以，就是这方面的证明的 ，T 类是可以比 output 类是短 ，T 类是可以比 output 类是短，那听起来很不错。但是就是我没有仔细看，所以有没有把我想做的东西做掉这样。所以还要再研究一下。那我找一下我们。等一下，我先。他好像，甚至是去年的那些结果我都没看到。对啊，他没上3位，他是那个 crypto eprint 上面的东西，所以没有3位。3位是看到开不是吧？对，他没有上来开。好，再上去打。 Okay, and let's go back and yeah, here is anyway, yeah, here is a quick derivation of y x convoluted with delta of n equal to x of n. And so we think about this identity system. So this identity system such that the output is always equal to input. And this is obviously an LTI system. So if this we have the identity system where y of n equal to x of n, this is an LTI system, and we can calculate its impulse response as well. The impulse response is a response to delta of n, and it should still be delta of n because this is identity. And so h of n will be equal to delta of n for identity system. And but we know that the LTI system is dependent by h, and so we have that when h of n equal to delta of n, then we are having the identity system such that y will so whenever h of n equal to delta of n, then this LTI system is the identity system. So y of n equal to x of n equal to x of n convoluted with so we should write the final result x of n, and that should equal to x of n convoluted with delta of n. Okay, so equal to x of n. Y is always for LTI system, y of n is always equal to h of n. X of n convoluted with h of n, and that's equal to x of n convoluted with delta of n. And I guess the easier way to say this is that for identity system, so I guess we don't need to go to the second line here. We can just say identity system y of n equal to x of n, and equal to x of n convoluted with h of n, and it's h of n equal to delta of n. Okay, so that's a derivation that x of n convoluted with delta of n equal to x of n for x of n, and similarly we have x of t convoluted with delta of t equal to h of t. So I guess I should write here. So similarly, x of t convoluted with delta of t equal to x of t. So convolute with the delta function if it doesn't change your input at all. So the delta function are kind of identity for this convolution. This is like multiplying one. I would like to think about it this way. Okay. And yeah, so that's oh, people are still writing. And anyway, I will reorganize this slide and publish a new slide later today. Okay, and but this is a very nice property to remember and know, and yeah, we will see variant of this throughout the whole course. Okay, so that's the identity system, and anyway, its application memories here says that. So we see that so if our impulse response is just delta, then it's identity. Then our response is some constant times delta. Then the output is will constant times the input, and this is obviously memoryless. Okay, that's for memoryless or memory, and for invertibility. For invertibility, so the derivation here we need a bit of HR statement here. So we have that if LTI system is invertible, then the inverse is also LTI. Okay, so it has a LTI inverse, and you can prove this in some problem, in homework problem, and anyway, if that's true, then we can show that the system is invertible. Then if only if So you can, if only if you have inverse on your system response, and I think this is very intuitive. So because this LTI inverse, since it's LTI, you also have some impulse. It can also be described by impulse response H1. So and you think about how H and H1 should convolute it together, they should be convolute to delta function, because this is how you get your system can be inverted by this H1. That's you have your system you have your input signal applying the first system and apply the second system, and they should go back to the original signal, and that's when the H and H1 convoluted together give you the delta function, and then we just show that any signal convoluted with delta function gives it to the same signal. And so I guess this is showing the if direction. So if this is true, then x excuse me, then we have found the LTI inverse. Then x convoluted with so the input signal x going through system with H, then go through the system with H1, go back to the original signal. And yeah, it should be not too hard to show that this is also only because this is not if this is not equal to delta, then this basically you think about this system. Then this system is not totally identity. Then there must be some input such that input convoluted with this system not equal to output. Okay, and yeah, so that's for discrete time, and for continuous time is very similar. So there is this inverse LTI system described by H1 such that H convoluted with H1 equal to the delta function. So you string those two systems together, you get the identity system. Okay, and here we have some example. And so our example, our system is very similar to identity channel, and it's called a time shift channel. So instead of the response just being delta function, then you have the response is delta function but with a time shift. So you have the delta of t minus t0, and yeah, so just similar to the identity channel, you can show easily by some argument show that the output of the system with this response is just input with a time shift. So while t equal to x of t convoluted with delta of t minus t0 will just equal to x of t minus t0. Basically we can. So your LTI system is very nice. So if you want to prove this, you can just do this in the invert way. So you just assume y of t equal to x of t minus t0. Then you say what's the delta of t. So what's the h of t of this thing? Then h of t will equal. So you put the delta as the input here. So delta of t as the input. Then the output is delta of t minus t0, right? So this is the proof of this is true. Because this system is LTI, and yeah, so first you need to prove this LTI, so that's not too hard. And once this is LTI, then you just calculate this h of t, and you see that the h of t equal to the response to delta of t, and that should be delta of t minus t0. Okay, so we see that delta of t minus t0 is the response to this time shift system. And back to our problem. Our problem is we want to see the invertibility of LTI system, and we want to find the inverse of this system, also inverse of this response. And the inverse of this response will be just delta of t plus t0. So just a time shift to the opposite direction. I think that's very obvious. Okay. And so you think about, so you have a time shift to the opposite direction, then y of t convoluted with h1 of t will be, you shift by t to t bypass to t0, then then you go back to while t plus t0 equal to x of t. And also, if you just convolute those two signals together, then you basically time shift this signal, and you get back to delta of t. Okay, so delta of t minus t0 convoluted with delta of t plus t0, and you get back to delta of t. And this is exactly the relationship we require here. Okay, so so those time shift systems are example of invertible LTI system. And then we have less trivial example here. So we have accumulator here, and they are also invertible. So H of n now is a very strong signal. Strong response is U of n. And then we can write down Y of n when our input is U, when our input response is U of n. Then we write down the convolution sum, so summation n from minus infinity to infinity. So we just change k to n for no good reason. We are summing over n here. Yeah. And anyway, so summation n from minus infinity to infinity, and then we have h of n minus m, and then you think about how does this u of n minus m look like. You see that it's non-zero only when m is less or equal to n. Okay, and so the summation is basically kept by n from minus infinity to n. So you are summing over x of n for n from minus infinity to n. And remember the independent variable here is actually n. So n now is located at the summation limit here. Okay, so u of n minus m, and you have n here. Okay, and anyway, this is our system. So you keep summing your x of n until some point n. That's your accumulator, and you want the inverse of this thing. You will be characterized by the LTI system with this impulse response. So it's a different system, so it's delta of n minus delta of n minus 1. And if you convoluted your y of n with your h1 of n, you see it's y of n minus y of n minus 1, because here we use multiple properties. So first we use the distributive property of the convolution. So y of n convoluted with h1 is y of n convoluted with delta of n minus y of n convoluted with delta n minus 1. Then we use that y of n convoluted with delta of n just back to y of n. Then y of n convoluted with delta of n minus 1 equal to y of n minus 1. This is just the property we just learned. So convoluted with delta function give you the same signal, and convoluted with time shifted delta just get you the same time shifted signal. Okay, so that's y of n minus y of n minus 1. Then you take a difference of this accumulation. You see that you get back to x of n. And the other way to check this is that you have the convolution between your h of n and h1 of n, and you see that it's u of n minus u of n minus 1, and that equal to delta of n. Okay, just like when we talk about the delta function, the unit step function. So so take a difference. It's kind of the inverse of this unit step accumulation. Question? If not, then let's go to the next property. That's causality. Okay, and causality is a weaker condition than memoryless, and it says that the system is causal if only if h of n equals 0 for less than 0. I would like to and the other way to say this is that the impulse response is 0 before the impulse occurs. And I think the derivation is very similar to the memory one. So you think about your system, when your input is O0, then the output should be O0 by linearity. Then you change the input to non-zero at n equals 0. Then because the system is causal, the response can only happen after this this impulse can hit at n equals 0. So the impulse should be non-zero only when n is greater or equal to 0. Okay. So I would like to think this. So my mental picture is kind of opposite of this thing. So it says it's 0 for n less than 0, and kind of the mental picture is that it's non-zero only when n is greater or equal to 0, because the input is always 0 before you hit it with something at n equal to 0, and so response can only happen after the response can only happen after the input. Okay, so that's causality. The response to this impulse can only happen after n greater or equal to 0. That means for n less than 0, the response should be always 0. And I guess that's only if, and for the if duration is also not too hard, you can just convolute something with this thing, and you see that the response will never give you the response should never depend on something in the future. You just need to think about the convolution a bit more carefully. Okay, if only if. And so for continuous time case, it's very similar. So the system is causal if only if h of t is 0 for t less than 0, because you hit the system and with a spike at t equals 0, and the response can only happen when t is greater or equal to 0. Okay, so that's intuition. And excuse me. And here we have some equation. And here is the other part of the proof. So you write down this convolution. Then you see that while when you have this summation, summation only to k from only minus infinity to n. So you don't depend. So while when don't depend on s of k. For k greater or equal to n. So while when only depend on past. Okay, and so here we have some example that we can ask you, test you later on. So say if h of n equal to u of n, is the system causal or not causal? And I guess we don't separate, but please don't cheat. And so if you think this system is causal, raise your hand. If h of n equal to u of n, is the system causal or not? You think this is causal, then raise your hand. And you think this is not causal, raise your hand. Okay, I think it's 1 to 1. And indeed this system is causal. Yeah, the answer is yes. And this is pretty obviously, this is I think this is pretty straightforward. It's because h of n, so you think, I think the only hard part of this question is you need to remember what u of n look like. So u of n look like this. It's a unit step function, and it's causal because it's the non-zero part only happen when n is greater or equal to 0. Okay, u of n, and u of n, this is a causal response. It's 0 when n is less than 0. And then the second part is more tricky. If delta of t equal, sorry, h of t equal to delta of t minus t0, is the system causal or not? Anyone want to answer? I think it's causal, then raise your hand. If you think it's not causal, raise your hand. Okay. I guess it's more correct if you say it's not causal. But this is a trick question because it depends on t0. Okay. So h of t equal to delta of t minus t0, and the function look like this is a spike at t0. So when t0 is greater or equal to 0, then your spike happen after t0, and so the system is causal. And then if spike is t less than 0, then it happened before t equals 0, and the system is not causal. And also we already know what this system is, right? This system is the time shift signal. And you think this makes sense? So when t less than t0, your system is delaying your output. So the system is a time delay system. So your input is delayed by some time t0. So that's causal. And but when t0 is less than 0, your system is a time dependent system. So your output is actually happening before your input for some t0. So that's not causal. Okay. So that's for causality. Then I think the next property here is the stability. Okay, and so this is a very confusing property, but so hopefully you can keep track of the details. Okay, and stability. Remember we have this complicated definition. So just before we talk about LTI, remember the stability. We have this quite complicated definition saying that stability means that if x of n is bounded, then y of n is also bounded. So we have this bounded input, bounded output definition of stability, BIBO. Okay, and so if we translate this BIBO stability definition to some property on h of n, then the property will be that h of n is absolutely summable. Okay. And similarly for h of t, it means that h of t is absolutely integrable. And absolutely summable means this equation. So summation k from massive infinity to infinity, the absolute value, so absolutely for this absolute value, and absolute value of h of k, and you sum it, and it's summable means that the summation is less than infinity. So you sum over the absolute value and it gives you a finite value. And similarly, for continuous time, you integrate over this absolute value and it's less than infinity. And I guess this is very confusing, so let's say the confusing part first, hopefully don't confuse you, is that we have a different condition here. So we have bounded here, and absolutely summable here. They all look like something bounded, but they are different. So being bounded is nothing as absolutely summable. And also remember, when we talk about BIBO, we are talking about a relationship between input and output. And when we talk about absolutely summable, we are talking about a condition on this impulse response, which characterizes the system, but it's also just a function. It also look like a signal. Okay, and yeah, so there is a difference between this relationship between x and y, and the difference between bounded and absolutely summable or integrable. Okay, but anyway, let's go back to a bit detail of this BIBO condition, and so I guess to give you some intuition of why we get this BIBO condition, we prove half of the statement. So we prove that if you excuse me, we prove that if your system is if the impulse response is absolutely summable, then the system is BIBO stable. Okay, and okay, so here we prove the sufficient condition. So if we have this absolutely summable, then we try to say it's BIBO. So when we have a bounded input, so this x of n is less than b for n, then y of n will equal to, now we just write down the convolution, summation k, h of k times x of n minus k. And here we already use some property of convolution. So remember, when we write down convolution, we have x of k, h of n minus k here. But here we use the commutative property of the convolution. So here this thing is actually, if you want to be very pedantic, this is like h of n convoluted with x of n. Okay, so we use a commutative property here. And anyway, so you write down this summation, and so you have absolute value sign outside for this absolute value. And but the summation of absolute value should less than equal to absolute value of summation should be less equal to summation of absolute value, and also absolute value of the product should be less than product of the absolute value. Okay, so you can have this less than equal to and have absolute value just on the h of k and x of msk here. And then we use this bounded input condition. We know that absolute value of every x of msk should be less than equal to b. So this is just less than equal to b times the summation of absolute value of h of k. And then finally we use this absolutely summable condition. We know this is a finite value, and a finite value times another finite value b, then this is a finite value. Okay, so we know that every y of n is a finite value. Absolute value of every y of n should be a finite value. Okay, so hopefully this gives you some idea about why h of k being absolutely summable is equivalent to x of n, and y of n. The system is BIBO stable, so whenever x of n is bounded, y of n will also be bounded. Okay, and just like what we do a lot in today, for necessary condition, we just upload to another textbook problem. So if you want to see the proof of this, you can try to do your problem yourself, and I think you can also find some answers online. Hopefully that's correct. Okay, and I guess let's see some example of this BIBO stable. And first example is once again this system we see a lot today. That's the pure time shift system. Okay, and so for the pure time shift system, the h of n is equal to delta of n minus n0 for different n0, depending on how much you want to time shift. Okay, and so you do this absolute sum of h of n equal to delta of n minus n0. Then you see that you are summing a whole bunch of things that's always 0, only when n equal to n0 this is 1, so this summation is just 1. Okay, I guess I'll draw this to make it a bit more clear. Okay, so this is h of n for this time shift is just at n0 you have 1, and it's at n0 you have 1 and it's 0 everywhere. So when you sum over everything, you just get this 1 here. Okay, and also for continuous time case, it's very similar. So for continuous time case, you have so instead of just 1 here, you have a spike with area 1 here, and so integrate through everything. And then you integrate through a spike at n0, then you get the area 1 of that spike here. Okay, so continuous time, the integration is also 1. So you see that both of the systems are stable. Okay, and that fit with our intuition about pure time shift being a BIBO stable system, because because the time shift, so your input is bounded by something, the output will be bounded by the same thing. You're just shifting the signal left and right, and obviously the highest point and lowest point of the signal is not changed. Okay, so pure time shifts are BIBO stable, and you see that their impulse responses are absolutely summable or absolutely integrable. Okay. And now we see unstable system. That's the accumulator. Okay, so accumulator we're seeing today is a system with h of n equal to u of n. Okay, and we can check that this is unbounded with two-way. Okay, and I guess we can see this unstable. First, by we already see this accumulator, so we will keep just adding things together. So if the input is 1, then the output will be input is always 1, and output is basically infinity. Okay, so the CCN is not stable because because the bounded input 1 will give you actually infinity everywhere. Okay, and You can also see this system is unstable by just looking at h of n, because h of n, look at this, right? It's u of n, and then you try to sum this thing for n from minus infinity to plus infinity, then you are summing over those 1 from n to 0 to infinity, and still infinity. Okay, and you can also consider an integrator. So this is something, this continuous counterpart of the accumulator, and so that's an integrator. That's y of t equal to integration from minus infinity to t x of tau d tau. So integrate the input signal from minus infinity to tau t. And the integrator will have the impulse response. The integrator will have the impulse response u of t. So it's very like you can see it's very like the accumulator. So because its response is both the unit step function, just change from the discrete time to continuous time. Okay, and so anyway, the response is u of t, and once again you try to integrate u of t from minus infinity to plus infinity, then you find out that you are integrating 1 from 0 to infinity, and that's infinity. And yeah, so this thing you check it 2 ways, it's unstable. So integrator, you put a bounded input, it give you a unbounded output, and also you see that its impulse response you see its impulse response is not absolutely integrable, and yeah, so you check both ways, the system is not stable. Okay. And yeah, so finally we give the review slide. Let's hopefully clear up some confusing points. Okay. And yeah, so first of all, once again, I want to emphasize that absolutely integrable or absolutely summable are different conditions from bounded or not bounded. And here we have 2 counter examples here. So first we have the delta function. We just see that delta function is actually absolutely integrable, because you integrate this function and give you 1. This is an example we get from this time shift, pure time shift example. We see the pure time shift, they have the response basically being delta function, and the delta functions are absolutely integrable, and the response is stable. And sorry, the system is stable with this response. And but obviously delta function has infinity at some point, and so this is not a bounded signal, not bounded function. And so we have another signal that's another direction. So we also see the unit step function. So we see the unit step function. Well, it's a bounded function because it's a function between 0 and 1, and but it's not absolutely integrable, because when you try to integrate this function, you get infinity, just like here. Okay, so yeah, please be careful, don't mix your idea of those things up. Being bounded and being absolutely integrable is totally unrelated. Well, I wouldn't say totally unrelated, but it's incomparable concepts. Okay, and yeah. Yeah, so those 2 concepts are incomparable. And remember, now we have 2 ways to check stability. And so chapter 1, we say the stability we define as this BIBO condition. So we say bounded input give a bounded output, then the system is stable, then the system is stable. And in this chapter, we give another way to describe stability. We say we can just check this h of t. And this is only good for LTI system, because only for LTI system the impulse response will totally determine your system. But for LTI system, you can check h of t, and you want h of t to be absolutely integrable or absolutely summable for discrete time system. And yeah, once again, here is a picture hopefully help you memorize the thing. So system map input to output. And the system will used to be just this arrow without any name, but now we know this arrow can be characterized by this h of t. So you can kind of see the system described by the h of t here, and we have two ways to describe scalability, either by a relationship just between this x and y. So bounded x gives bounded y, and that only happens when your h of t is absolutely integrable, or absolutely summable. Okay, so yeah, don't mix these things up. Don't try to say h of t is bounded, so the system is stable, etc. Okay, it's this thing you need to check integration or summation, and for the input output you need to check this is bounded means this is bounded. Okay, and I think we can. Okay, and we have a bit more things. It's a bit less important, so I think we can get go through them very quickly and maybe stop a bit early today. Okay, and then next this concept we have here is basically just a notation. So we have the unit step response of a LTI system. Okay, here I think here we won't use this concept too much, but it's nice to know the name here. So unit state response is very similar to unit impulse response. So remember we have a unit impulse response h being the response to the delta function, and the unit state response similarly is the response when the input is the unit state function. So u of n or u of t. Okay. So yeah, basically the most important. I guess there are two important notations to remember. So first is the unit state response. Okay, so this name, I think this name is very intuitive. It's a response to a unit state function, and also at least in the textbook and in this course we'll use the notation s of n as a unit state response. So we use h as a response to delta and s as a response to u. Okay. So unit state response is written as s of n or s of t. And excuse me. And then we see that. So here we can do some derivation. So we can convert s of n and convert back and forth between. Actually, we can convert back and forth between h and s with a quite nice relationship. So for the discrete case, we see that s of n is a response to u of n, and so that should be u of n convoluted with h of n, because the output with u of n, well, that's just any output of the system is the input convoluted with h. Okay, and so that's u of n convoluted with h of n, and by commutativity of convolution, that's h of n convoluted with u of n. And so you do this, then we view this as a accumulator system, and then we see that that's accumulating your h of k from k minus infinity to n. Okay, so h of n is like summing over your h of k up until n. And then since this is accumulator, then we already know the inverse of accumulator is the h of n is just s of n minus s of minus 1. And similarly for continuous time, you have s of t equal to u of t convoluted with h of t, and that's h of t convoluted with u of t, that's the integration of h of t, h of tau up until t. And then you want to inverse this integration, you can do differentiation. Okay, so yeah, so basically you can either describe your system by h or describe system by s. But in the course, we'll mainly focus on describing h. Okay, and so that's one thing. Nice to remember the name unit state response. And second thing is we can think a little is a bit more intuition about what convolution do. So we think about convolute input signal with some impulse response, and we see that the support of the support of the output signal will get longer. And but first we need to say what support. So we have this mental picture that our input only happen at some finite time, because just because you think about, now we kind of go back to physics. So we think about, we hit the system with some physical signal, but well, people have a finite lifetime, so you just do your experiment in some finite time period, right? Maybe from today to tomorrow, etc. Okay, and or more like maybe from the start of your class and the end of your class. That's when you do your experiment. And so your input signal is confined in some finite period, and outside of this period, the signal is all zero. Okay, and so this time period is called the support of your signal. Okay, so your signal is all non-zero between this T1 and T2. So that's like the start of your class and end of your class. Say you are doing some experiment for the class, and okay, and you can similarly define the support of your h of t if it's finite. Okay, so say your response is some nice response that it has some finite time period, t3, t4. Then you can easily see, calculate that. So your output is this x convoluted with h. Then you see that outside of this range, the y of t will be 0. So your support will just be, your y of t will be supported on t1 plus t3 and t2 plus t4. So basically the left boundary adding together and the right boundary adding together. So your support of x is t1 and t2, support of h is t3 and t4. Then the support of x convoluted with h will be t1 plus t3 and t2 plus t4. And obviously that means that the possible length of your y of t will be the input length plus the impulse response length. Okay, and similarly for discrete time case, you will have that. For discrete time case, you also have the support of the output is n1 plus n3 and n2 plus n4. And the length counting is a little different, just because the discrete time, the length is n2 minus n1 plus 1. Okay, so that's just elementary school counting. Okay, and anyway, the length of the output is similar to, is also very close to the length of the signal plus the length of the impulse response. But there is a HR minus 1 just because there is some issue with the plus 1 here. Okay, that's about support of the output signal of LTI system. So the support will get the support of basically the support of the response will get added to the support of the input. And I think that's all I want to talk about today. And next class we are going to a bit of application of our analysis of LTI system. That's we are going to use it to solve differential and difference equations. And this will actually be a recurring thing of this whole course. We will see as we get better and better analysis, we are going to solve more and more complicated differential and difference equations. Okay, and I think that's a major application of our analysis of LTI of signal and systems. Okay, and yeah, so I guess we can stop a bit early today, and we'll continue on Thursday to describe those solving equations. Okay. Yeah, so see you on Thursday.